This is a graph of the annual declination of the Sun. As you can see, it looks sinusoidal in form. It would be a perfect sine wave if the Earth's orbit were truly circular. In practice, because the Earth's orbital ellipse is so close to circular, the graph is very close to sinusoidal. The declination of the Sun can therefore be considered to follow a sine wave, with a peak amplitude of 23.5 degrees and a cycle of 1 tropical year. The Sun appears vertically above 23.5 degrees south on the 21st of December. This is known as the Northern Hemisphere winter solstice and the Southern Hemisphere summer solstice. It then crosses the equator from south to north on about the 21st of March. This is known as the Northern Hemisphere spring equinox and the Southern Hemisphere autumn equinox. On the 21st of June, it will appear above 23.5 degrees north at the Northern Hemisphere summer solstice and the Southern Hemisphere winter solstice. And on the 21st of September, it crosses the equator from north to south at the Northern Hemisphere autumn equinox and the Southern Hemisphere spring equinox. These dates are not always exactly on the 21st of the month. This is partly because the precise date depends on the relationship between the year considered and the leap year cycle, partly because our calendar does not have the same number of days in each month, and partly because the orbit is elliptical, not circular, and the Earth travels at a different rate at different times of the year. However, the difference is never more than a day or two. The length of the hours of daylight at any particular latitude varies with the declination of the Sun. The rate of change of the length of daylight will therefore be greatest when the rate of change of declination is greatest. You can see that between about the 7th of March and the 7th of April, the declination changes by 20 degrees. A similar situation occurs around September the 21st. Therefore, the rate change of the length of daylight will be greatest at the spring and autumn equinoxes. At the summer and winter solstices, not only is it the flattest part of the curve, but it is also changing direction. There is hardly any change in declination, and therefore very little change in the length of the hours of daylight. This explains the origin of the words solstice and equinox. Solstice comes from two Latin words, sol and sticere, which means sun and to stand still. To the ancients, it seemed that the sun was standing still at midsummer and midwinter, because at those times of the year the days did not appear to change length. The word equinox comes from two Latin words meaning equal night, because at the spring and autumn equinoxes we get closest to 12 hours of daylight and 12 hours of darkness. Just as declination is the celestial equivalent of latitude, we also need a celestial equivalent of longitude in order to define the position of a body in 2 dimensions. This is called hour angle, and it is defined as the arc of the equinoctial between a datum meridian and the meridian of a celestial body. It is similar to longitude, except that it is always measured westwards. Let's look down on the Earth from above the North Pole. We choose a datum meridian. As the sun or star transits the datum meridian, the hour angle is 0. In this example, another celestial body is 80 degrees west of the datum, so its hour angle is 080. Here we see the Greenwich meridian being used as the datum. Position 3 has a Greenwich hour angle of 050, which corresponds to longitude 50 west. Position 4 has a Greenwich hour angle of 180, which corresponds to the Greenwich anti-meridian. And position 5 has a Greenwich hour angle of 270, which corresponds to longitude 90 east. Note that it is not necessary to say 270 west. It is always west. If the hour angle is measured from the observer's meridian, it is called the local hour angle and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle and abbreviated to GHA. Because the Earth is rotating, the hour angle is constantly changing and is only valid at a specific time. By contrast, declinations of stars are constant for many years. Even the Sun's declination can be regarded as constant over a period of a day. Let's summarize this lesson. The Earth's orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. The plane of the orbit of the Earth round the Sun is called the ecliptic. However, the Earth's spin axis is at an angle of 66.5 degrees from its ecliptic. The plane of the Earth's equator extended out into space is called the equinoctial. The angle between the equinoctial and the ecliptic is therefore 23.5 degrees. The Earth's orientation in space does not change significantly and can be taken as constant over a period as short as 1 year. What does change, however, is its orientation relative to the Sun. Declination is the celestial equivalent of latitude. Seen from an Earth-centered point of view, the Sun's declination appears to change like this over the year. This annual change of the Sun's declination explains the seasonal variations in temperature. It also defines the Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn at 23.5 degrees south. They are the highest latitudes that the Sun can ever be directly overhead. The annual change of declination also explains the variation in the hours of daylight at different latitudes throughout the year. This gives us the definition of the Arctic and Antarctic circles, at 66.5 degrees north and south. They are the lowest latitudes at which it is possible to have at least 1 day a year of continuous daylight or continuous darkness. The graph of declination is very close to a sine wave. It gives the most rapid changes in the length of the hours of daylight at the spring and autumn equinoxes, in March and September. The longest and shortest days occur at the summer and winter solstices. Just as declination is the celestial equivalent of latitude, hour angle is the celestial equivalent of longitude, in order to define the position of a body in 2 dimensions. It is always measured westwards. If the hour angle is measured from the observer's meridian, it is called the local hour angle, and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle, and abbreviated to GHA. Declinations change relatively slowly, but hour angles change continuously as the Earth rotates, and must be referred to a specific time. This completes the second lesson on time. The next will look at the various forms of time used in order to cater for longitudes other than Greenwich.